In this next one, we're going to look at elastic potential energy. So we have a bungee jumper jumping off a 20-meter bridge, and we're asked, given the elastic constant of the bungee cord, how much the bungee will stretch if it stops them just before they hit the ground. So if we can imagine, this is our little bridge here. We're going to jump off. This is maybe how long the bungee jump or the bungee cord would be if they were just hanging there. And then this is how much it's going to stretch. Okay, so we'll call this x. And so here we're trying to find out what x is. And then we'll call this total height here 20 meters. Okay? So when we work on a question like this, this is, a great problem to use energy for, because we can say that their gravitational potential energy they had at the top of the bridge is going to be transformed into elastic potential energy at the bottom. So we can start by just doing a diagram. We'll say that our system here is the jumper. Okay. That looks really pretty, so you're welcome. We can also say the bungee. And the reason we're going to include the bungee is because we want to say that some of the energy is going to store there. And so we want to keep track of that energy. And then we can also say the earth is part of our system. Alright? And so let's make an LOL chart. So the type of energies we're going to look at here, we're going to look at the jumper is going to jump, so he's going to be moving at some point, so maybe he'll have kinetic energy. Okay, we're going to have a change in height, so energy from the earth is gravitational potential energy. And then finally, energy is going to be going into the bungee, and so that will be elastic potential energy. So U sub S. Okay, so to start, if he's just standing on the bridge, he doesn't have any kinetic energy. He would definitely have gravitational potential energy because of his height above the ground. And there would be no elastic potential energy because the bungee is not stretched yet. Okay, and after he jumps, that gravitational potential energy is going to transform as he's falling into kinetic energy. Okay, but something's going to happen right here. The spring is going to start to stretch. Okay, and he's going to be slowed to a stop. Okay, which means that if we're looking at just at the very top and at the very bottom, then the kinetic energy at the bottom will also be equal to 0. So we essentially don't even need to look at the speed of the bungee jumper at any point. Okay, this is assuming that it's a closed system, meaning energy isn't lost to things like air resistance. Okay, and so at the bottom, there's no more gravitational potential energy because the height has decreased to 0, and everything left has gone to elastic potential energy. And so what we can say is that the gravitational potential energy decreased as it was transformed into elastic potential energy. So we write our equation. We can say 1/2 mv squared for kinetic plus mgh for gravitational potential energy plus 1/2 kx squared for elastic potential energy equals 1/2 mv squared for kinetic plus mgh for gravitational potential energy plus 1/2 kx squared for elastic potential energy. So we can go through and say, okay, well, this is equal to 0, and this is equal to 0 because we had neither of those at the beginning. At the end, that's 0 and that's 0. So we end with this and we started with this. So we can rewrite the equation like this. Okay, mgh equals 1/2 kx squared. And now we're going to be solving for x. So we can multiply by 2, divide by k, and then we'll finish by taking the square root of both sides. And so x will be equal to the square root of 2mgh over k. If you punch this in your calculator, you're going to find that the stretch is about 4.4 meters. Okay, so he's going to jump, and get to about here, and the bungee cord will start stretching, and it's going to stretch a distance of 4.4 meters as it brings him to a stop. Okay, I did make one mistake earlier when I said that this distance right here was the distance of it when he was hanging there on it. This is actually the distance when nothing is on there. Okay, and so anyway, it's going to stretch 4.4 meters.